Okay, so here's what we got today. We're going to go over this whole concept of what happens when electrons produce light. Then we'll go do what's called that flame lab, which is kind of like what I did yesterday with the Bunsen burner, and you heat up the chemicals and do that. So that's what we got today. Review tomorrow, midterm on Friday. So here's the main idea that you have to get, okay? Yes?
Is the midterm multiple choice?
Mostly,
Oh, hallelujah.
but not all. Okay? Mostly multiple choice.
Thanks, Mr.
Now, and I'll ask this because it doesn't make me any difference. So one option is that I can give you a Scantron and you can vote on the Scantron. Shh. Okay? Or the other option is that I give you like just a sheet of paper and you write the answers on that. It doesn't make me any difference. Which do you prefer?
Sheet of paper.
Okay, good, because that's easier for me to grade. Okay, because that way I got, because of the Scantron, I got to walk down to the office, I got to run them through the machine, and then I just have to go through them anyway. So, all right, I'm just going to give you all a piece of paper. Okay,
Weird green thing.
so here's the main idea, is that when you look at light, for example, this white light is composed of all these different colors, okay? And if you can sort it out, you would sort it out into these colors of Roy G. Viv. All the way down, red, orange, yellow, all the way down to violet, okay? Here's what you have to remember in terms of extremes, okay? So red light has the longest wavelength, it has the lowest frequency, and it has the lowest amount of energy, okay? Remember your extremes. Red light, that's the last color a fire glows before it goes out. So red light is the lowest possible energy state. Violet light is the opposite extreme of that. That has the shortest wavelength, it has the highest frequency, and it has the highest energy. So as you go through this spectrum of red down to violet, you're going from low energy state to a higher energy state, okay? So here's the other thing that you have to understand. When we talk about what's happening inside an atom, we cannot take a snapshot and go, oh, look, here's the nucleus. Oh, here's where the electrons are, okay? We can't do that. Cannot do it. And here's the reason why. Because, bless you, if you're going to try and see an electron, okay, if you're going to try and see, it's like, oh, we'll look at an electron. So what's known as the Heisenberg uncertainty principle. So if you're going to see an electron, you have to hit it with a bundle of light. So if you look at what's happening, for you to see what's happening in this room, or anything that you've ever observed, what happens is that these lights give off photons. Those photons then get reflected off. They enter your eye gets that information. It actually flips the image upside down. You are actually seeing me upside down right now, but your brain flips it back over. And you says, oh, Mr. Burkamp is wearing a white shirt today. Okay? So the reason my shirt looks white is because of the fact that it's reflecting all of the colors. Okay? It's reflecting all of these. Now, Emma's shirt looked kind of reddish pinkish. Okay? The reason that looks reddish pinkish is because of the fact that her shirt is actually absorbing every color but that, and that's what's getting reflected off. Okay? If you're wearing a black shirt or black hoodie, okay, what's happening is that you're absorbing that light, and not very much of it is being reflected off. So what you see as a color is actually the fact that it's absorbing every color but that. So what that means is if this light that was being emitted, let's say it didn't have that particular shade of like kind of a fuchsia pink, your shirt would actually appear black because there would be no light that would reflect off of that. So if this light didn't have the color of your shirt would appear black. So what's happening for you to see anything, the flame test that you're going to do today, is because electrons have to get excited, move out of their ground state, and emit light. So that's the two ways that light gets, that you can see anything. Either it gets reflected off or it gets produced at a source. The lights are producing the light. They're exciting these electrons. They're emitting photons. The photons are being kicked out. They're hitting your shirt. They're bouncing off. You can see, whoa, Bergkamp's wearing a white shirt today. Okay. So if you can take that and separate it out, that's what's going to happen. So if you're going to, quote, see an electron, okay, goes back to the story. If you're going to see an electron, a photon of light would have to bounce off of it. Okay, here's the problem. Electrons are so very, very small. That would be like you trying to see a mosquito and hitting it with a sports car going like 300 miles an hour. Okay? It's like, oh, I know where the mosquito was. I don't know where he is now. Okay? Because we hit him with so much energy that it completely messes up the mosquito. The same thing happens with electrons. If we try to see an electron, we have to hit it with a photon of so much energy that it completely knocks it out of its orbit. So by finding it, we no longer know where it is. That's the irony of it. And that's what's known as the Heisenberg uncertainty principle, usually written as HUP, Heisenberg uncertainty principle. So what we can't figure out, and this is what you're going to see in the lab, is that if we make these atoms get excited, okay, and those electrons are in that ground state, they move up to, so the two things, listen to me. The two things that have to happen for you to see light emitted from a source, you have to take electrons from their ground state, move them up into an excited state, and then they don't like it there, and they come back down. And in the process of coming back down, they're going to emit some form of energy. Okay? That's your process. I promise you, I promise you, I promise you. So when you see something, an electron moving from the ground state up, you absorb energy. When it comes back down, it emits energy. So what we've seen is that once we take this light and we separate it out, every element has its own unique spectrum, its own band of colors. So what this is showing you over here on page 2, okay, what it's showing is that there's two possible ones here. You have hydrogen and you have boron. So hydrogen is a 4-band spectrum. Okay, this is what we call an emission spectrum. So if you take hydrogen gas and you run an electric current through it, it's going to produce a certain flow of light. And if you take that light and you separate it out, this is what you would see. So you would see a band of red, bluish green, bluish violet, violet. And again, here's the deal. We don't know what's going on with these electrons. But here's the quintessential thing. Because each element only emits certain colors of light, what that means is that these electrons can only absorb or emit certain amounts of energy. Okay? It's not a continuum. So it's like, here's the electrons in the ground state of hydrogen. So they can have a certain amount of energy level here, there, okay? And that's it. They do not exist in between. So either you give it enough energy to move up to that first energy level, and then it's going to come back down, or it doesn't move at all. And it doesn't even exist in between. Like it ceases to exist at the ground state, it literally disappears, and then it reappears in a higher quantum state. And then a higher quantum state, and a higher quantum state. But then to come back down, it's like, ooh, I got this energy, man. I can't be in this high of energy level and be here. I've got to get rid of this energy. So it'd be like it's 10 o'clock at night, and you know you got this big event going on tomorrow. Maybe it's a dance recital, maybe it's a sporting event, whatever excites you, okay? And it's like, you know, there is no way you're going to go to sleep. It's like, man, I am just too wound up. You are in this excited energy state, and there is no way you're going to go to sleep. It's like, okay, do yoga, something, listen to that, whatever alarm what was going off this morning on his other phone, okay? Maybe something soothing music. So you've got to get rid of that energy so you can return back to that ground state. And that's what the electrons have to do. They're going, oh, this isn't good. We're in this excited state. Mother Nature's a lazy prima donna. Mother Nature goes, you cannot return back to that ground state unless you get rid of that photon. Okay, so it's just like your mom, imagine this, you come home and you're all wound up. Woo, Mom, that's cool, right? And Mom goes, I am not letting you back in this house until you calm down. Okay, and that's basically what Mother Nature says to the electrons. You are not returning back to this ground state, young man, until you get rid of that excess electron. And the electron goes, whoa, mom, chill out, okay? Chill. I'll get rid of it. And the only way you can get rid of it is by giving off a bundle of energy, okay? So, got that idea. So, what I want, so on this one, so for example, on number 8 on page 2, this is spectral lines for hydrogen gas bicolor and the corresponding wavelength. Okay, so hydrogen has a pretty simple spectrum because it only has one electron. It can't be that complicated. So all I want you to do on that one is say, oh, red's at 656, and these are measures of length called nanometers. Okay, nanometers are just measurement of length. So you're going to have red, the blues, and violet. So you should have 4 lines. Now on number 9, boron's much more complicated because boron has a lot more electrons than hydrogen does. So boron's wave pattern or emission spectrum is a lot more complicated than hydrogen is. And all you want to do, list 3 of them. I don't care which ones you pick. Pick 3. Write down the colors and the wavelengths that go with it. That's all you have to do. So, and here, and you'll notice that they kind of reinforce this idea. So when you get to question number 10, says which color of light corresponds to the shortest wavelength? Is it violet or is it red? Which color of light responds to the longest wavelength? Is it violet or is it red? Those are your 2 choices on question number 10 at the bottom of page 2. It's either violet or it's red. Now, and then the same thing is going to happen in number 11. Now you're talking about energy, okay? And again, your choices on number 11, A and B, are either violet or red because you have opposite ends of the spectrum, okay? So on 11, A and B, your answer is either violet or red. Now, here's the deal. When you get to number 12, gas discharge tube, basically you take this gas, you excite it up, okay? And that's how you produce this light. It says, are these going to produce the same? And it's not, because of the fact that the spectrum of boron contains different colors than the spectrum of hydrogen does. Okay, that's all you have to say on number 12. Don't make it complicated. And then when you get to question number 13, spectral lines are like a fingerprint. How do the spectral lines for hydrogen and boron support this statement? All you have to say is that the spectral lines of boron are different than the spectral lines of hydrogen. Okay, that's all you have to say. Don't make this complicated. But, and this is what you're going to see from this lab today, is that each element, when excited, produces its own unique color. So that's what I tried to show you yesterday with the flame test. Now, this also ties in this idea of Coulombic forces. Okay, so I want to make sure everybody's cool with this. Questions on 14. Electrons and protons, attract, repel. Grace, attract, repel. Electrons, protons. Why?
They're opposite in charge.
Opposite the charge. Fantastic. On 15, as an electron gets closer to the nucleus, okay, does the attractive force get stronger or weaker? Ella.
Stronger.
Fantastic. You shrink the distance, you increase the force. Here's the heart and soul of this. Alec Grill, what's your answer to number 16? For an electron to move from energy level close to an energy level farther away, does it gain energy or lose energy?
Gain.
Fantastic. So then, if it's going to come back down, it's got to lose energy. That is some of the most important things you have to understand from this. Now, when you get to that diagram on 18, okay? So on 18, this is like this Bohr model. So you've got this nucleus, and then you have this series of concentric circles which are representing energy levels. In reality, we don't know where the electrons are, but this is a good model because they're actually moving waves, but that's a whole other story. So, you have an electron going from this point up to there. Gaining electrons, or excuse me, gaining energy, losing energy. Ramen.
17, lose.
No, 18. The diagram down below.
What's the question? Sorry, I was not.
It's moving an electron from a lower energy state to a higher energy state. Is it absorbing energy or giving off energy?
Giving off energy. Absorbing it.
Yes, because it's going from a lower energy state to a higher energy state. Okay? Now, when you get to page 4, okay, I want to make sure everybody's cool with what's happening on page 4. So, what this is showing you is the 4 transitions that are possible to create the 4 spectral lines of the hydrogen atom. Okay? This is the heart and soul of this. So we had to come up with a mechanism to explain, like, man, why does hydrogen only have 4 potential energy levels? And again, this is where this all comes into being. If you know the light that's emitted, and you know that E equals HF, okay? So if you know the frequency of light that's emitted, multiply that by Planck's constant, then you know the energy. So what that means is that's how much energy difference there is in between the energy levels. So if you look on Model 3, question A, part A, notice that the light that's emitted there is the shortest wavelength. So that transition then, if you look at this, look at this one. You're going all the way from n equals 6 all the way down to n equals 2. So that's a big jump. You're going from 6 to 2. That's a big transition. With a big transition, that's a lot of energy. With a lot of energy, guess what? That's going to require a higher frequency and a shorter wavelength. So what you should see on A, that's the one that's producing violet light, because that's the one that's the most energy involved, because that's the biggest change. Then you're basically working your way down. So you're going from B, you'll notice on B has a slightly longer wavelength. C has an even longer wavelength. D has the longest wavelength of all of them. So basically at this point you're going, wow, do you understand that a shorter wavelength requires more energy, and therefore that's a bigger jump? That's the whole point of those series of questions. So then when you get that, answering 19 should be pretty simple. You're going from n equals 5, list the corresponding colors of light emitted, you did that. And then the electron transitions, are they releasing energy or are they absorbing energy? That's what you want to look at. Okay. Now, on page 5, all you're doing is kind of summarizing this thing. Which of the electron transitions involves the most energy? Is it A, B, C, or D? That's all you have to do. So here's how you can figure that out. You can either visually look and see the difference between the energy levels, or you could find the one that has the shortest wavelength. Whichever one that you want to do, it's going to be the same answer. Now, when you get to B, I don't like B. We need to change, this will make more sense. On B, it says, explain why the transition involves the most energy based on your understanding of the attractive forces. Okay? This is all about energy. Okay? It's kind of weird how they put it. So basically what happens is that when you take an electron in the ground state and you lift it up, it's like you're storing energy. So if I take this apple and I just lift it up a little bit and I let go of it, it's going to return back to its ground state. Okay? But since I didn't lift it up very far, I didn't store much energy, so I don't have much energy when it lands. Now, if I lift it all the way up to here and I drop it, because of the fact that I have to go against the force of gravity that's holding it there, that's going to store more energy. So basically, the farther you move an electron from its ground state, because of the fact that it has an attractive force, so the farther you lift it up, the more energy that you store. So it's like stretching a spring. The farther you stretch a spring or a rubber band, the more energy that you store. So that's how some visual, if you're a visual person, imagine that this electron is here, and you're going to grab a hold of it, and you're going to stretch that rubber band. And the farther you stretch that rubber band, the farther you move it out of that ground state, the more energy that you're going to store, and then you're going to let go, and whoop, bam, it's going to come back down to that ground state. So that's the easiest way to explain B. Say there's an electron, it's attracted to the nucleus because they have opposite charges. The farther you stretch it, the more energy that you store, the more energy is going to be released when that comes back down. Okay. Anyway, so here's the heart and soul of question number 22. Explain why a single atom of hydrogen cannot produce all 4 hydrogen spectral lines simultaneously. Okay? The reason that you can't produce all 4 lines at once is because of the fact that how many electrons are in a hydrogen atom? Do not make this difficult. How many electrons are in a hydrogen atom? Miles.
1.
1. Okay? So 1 electron can't make all 4 transitions at once. Okay? At most it can make 1 transition. But if you have a whole bunch of them, then you can produce all of the spectral lines because you have a whole bunch of electrons that are capable of making that jump. Okay? So those are your answers to basically 22 and 23. Single electron can't make them all at once, then you get 23, but if you have a large enough number of them, then you can produce all of them. Now, on that last page on number 6, okay, this is like an application kind of thing. And on 24, all you're doing is proposing. So, here's the deal. And let's look at A and B. So, on A it says to propose a hydrogen in that transition that involves light with a wavelength in the ultraviolet range. Now, we can't see in ultraviolet, okay, which is a good thing, because if we could see in ultraviolet, then it would just be like sensory overload. Ultraviolet light is important. Ultraviolet light is what causes you to get sunburned when you're outside. Okay, UV light has more energy than normal visible light. So remember this: UV light has a higher frequency and a shorter wavelength than visible light. Okay, so look at this in terms of transitions. On this last question, you want to produce really high energy photons, okay? Is that going to require a really big jump or a really small jump? Miles.
Big jump.
Big jump, okay? Pick big differences between energy levels. That's all you have to do. Then on B, you're talking about infrared, okay? Infrared light is what you feel as heat, okay? So like yesterday when I had the nichrome loop, and after it stopped glowing, it still felt warm. Okay, it still felt warm because it was producing infrared energy. So infrared is the opposite. Infrared has a longer wavelength than what we can see. That's why with a longer wavelength, that's less energy. Pick a small transition. Okay, that's all you have to do. Now, when you get to 25, so 25, you have the 4 different lines of lithium, hydrogen, helium, and sodium, and then the unknown is a mix of these, okay? So what's happening on 25, basically you have this series of lines like this, okay? Ding, 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 boom, 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 okay? So this unknown down below is a mixture of 2 of these. So basically, if you want to know what's in there, and some of these are pretty close together. You might have to take like a straight edge or like a piece of paper and make sure that they line up. So basically, take your unknown down below and take that line and transpose that going up. If you can find that line in that emission spectrum of that element, it's there. If you can't find that line in that emission spectrum, it's not there. Okay? That's simple. So what you should see on 25A, there's 2 elements that are not there and 2 elements that are there. Okay? Now, on 26, this is the opposite. It's called an absorption spectrum. So, an absorption spectrum is actually tougher to do. Okay? I mean, just, it's tougher to do. So, on an absorption spectrum, it's like the opposite of an emission spectrum. So if you have an emission spectrum, you might have like 4 lines, okay? Because that's the light that's being emitted from the electrons. An absorption spectrum is like the opposite. So what you do with an absorption spectrum is that you take a sample of hydrogen gas and you shine light on it. You shine this whole spectrum of light on it, okay? And then what happens is that the electrons that can absorb that particular amount of energy do that, so they soak that up. So what you would see on the other side is that you would see this continuous spectrum, but then you would see gaps where the electrons are absorbing that energy. So instead of having basically no lines and 4 distinct lines, it's just the opposite. You would have this continuous spectrum, and then you have gaps where the electrons are acting like a sponge and they're soaking up that energy. Because they're soaking up that energy and then they're going up to that higher energy state. So it's just like the opposite. So an absorption spectrum is like the opposite of an emission spectrum. So you would, instead of having like a 4-line emission spectrum, you would have a continuous spectrum with 4 gaps. That's the basic idea. Okay, are we all better in terms of this packet? Yes, ma'am. You shake your head no.
So what are we supposed to write for 24? Like, what is it asking us to do?
Like propose a mechanism? Like for that one with the UV?
Yeah.
Okay, so go back to that diagram on model 2, okay, which is, whatever model 2 is, down here on, like on the bottom of page 3, okay? So here's the deal. You have 6 potential, imagine this is like an onion, and you have 6 layers to the onion, okay? And imagine that at the bottom is like the lowest potential energy. That's that first layer of the onion. So if you just lift something up to the second energy level and let go of it, is that going to be very much energy?
No.
No. But if you take it from n equals 1 all the way up to n equals 6 and let go of it, then that's going to produce a lot of energy. So if you want UV light, you have that biggest jump from like n equals 6 to n equals 1. If you want infrared, that's just going to be a smaller jump. So you could pick maybe like n equals 5 to n equals 4.
So I'm just writing n equals to n equals?
Yeah, that's all you have to do.
Oh, okay.
Yeah, that's all you have to do. Do not make that complicated. Yes?
How do you do like the 25 and 26? I'm so confused.
On which one?
25, A and B. What do we write?
Okay. So let me draw that a little bit more clearly. Come on. So let me pick on one particular line of lithium. Okay.
Oh, because you're going.
So here's the deal. So let's start with lithium. Okay? So lithium is a 4-line emission spectrum. Okay? So pick any of them. Let's talk about this third one over from the right. Okay? So there's an electron within the structure of the lithium atom that will emit this particular amount of energy. Okay? Now, if that is there in this unknown, if lithium is in the unknown, when you look at this line, that spectrum line is going to be here. So go to lithium, find this third one over from the right. Now, go straight down to the spectrum line of the unknown. Is that line in the unknown spectrum line? it's not. So that means lithium is not there. But if you go to like hydrogen, and if you find the lines that are in hydrogen, and you bring that straight down, you'll find that the hydrogen lines are there. So basically, it's just lining them up and moving them down and seeing what's there. Got it good, Grand? Okay. Stop that for a second. So, what we're going to do is we actually have to go down to Miss Schertz's room because we can't use the room next door. So, what you're going to do is you're going to take these splints that have been soaking in these different chemicals, you're going to put them in a Bunsen burner, they're going to light up, they're going to emit light. It goes pretty fast. So what you want to do, like for example, you think the first element contains sodium, okay? And it will say, like, you're going to know what these are. You're going to know, oh, these are, it's soaking in potassium chloride or whatever it is. So over here you've got the spectral line. So up here in the right corner, start that back up.
Oh, I did.
Oh, you did fantastic. You're the man. So what you want to do here is figuring out what the spectral lines of sodium are going to look like. So what you got to do is go into Google Classroom. I know it's rare that I tell you to do this, but if you go into Google Classroom and then come down here towards the bottom, da 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 da, way down here. Of course, what I need is at the very bottom of this thing. Okay, so once you're in Google Classroom, if you go all the way down, this is what we're going to do today, is this flame test live. So, to figure out these emission spectrums, it's going to say, use the following link. Okay, so all you have to do is click on that. Doink, there you go. So here's the cool thing about this particular, this is where technology is pretty cool. So if you come up here and you're going to get a periodic table that's going to look like this. So let me turn on the light so that's easy to see. Little mood light. So if you type on like sodium, so what this is showing you is what the spectral lines of sodium look like. So the cool thing about this is that you can pick any of these. So one of the ones you're going to do a lot on this particular lab, like you're going to have copper, which is come up here and you hit copper. Okay. So, and I'm going to have colored pencils, or you can do this on your own. This doesn't have to be something that you do in the lab, but it does have to be later on. So this is how you're going to figure out what the spectral lines of copper is going to look like. So you've got like a violet, a blue, a couple of greens, a couple of yellows, that's it. So what you'll see is that we actually don't have that many solutions that we're going to use. We have different cations and anions. Remember, what's the difference between the cation and the anion? Which one has the positive charge, the cation or the anion? Cation. Now, anions have the negative charge. So, let me see this. When you get to question number 11, okay, one of the things you're going to do is that you are going to use strontium, okay, which is in this group 2. And the one for strontium is very, 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 very complex because strontium has this big electron cloud, so it has a lot of lines in that spectrum. So on question number 11, I'm asking about strontium chloride. So with this one, to save you some time, you could type in the formula for strontium chloride, but let me save you some time. So on number 11, the formula for strontium chloride is SrCl2. Okay, so on number 11, you got strontium chloride. And then on number 12, you need potassium nitrate. And again, just to save you some time, That's the formula for potassium nitrate, KNO3. And then on 13, you have potassium chloride, which is KCl. I think all the other ones, the formulas are there. Yeah. So on these ones, strontium chloride, SrCl2, potassium nitrate, KNO3, potassium chloride, KCl. That will save you some time. That way you have the formulas. Okay, so stop that. We're going to